recording right now, and we are resuming the discussion of um, the device that can remember things, which we call the SR latch. So that's where we left off last time, and that's where we are going to continue today. Right. This is from my other class. I'm going to switch back to this class. Well, before I go any further, are there any questions about the homework assignments? The program to do the conversion from base 10 scientific notation to something that's kind of resembling the double precision floating point number, but not exactly. So are there any questions about that? Today is the 11th, so it is time. It's past due right now, okay? We are just probably about a minute and 20 seconds past due, nonetheless past due. So are there any questions about this homework assignment, the negative exponent assignment? So you guys got it done? Yep.
So I ended up getting mine done, got the same result and everything, but I noticed in one of our headers, we were given access to UN64 underscore max, I think is the exact one.
Yep.
Were we able to use that?
Yeah.
Okay, because
Yeah.
some of the people I was talking to were defining their own max.
They can, it's just not necessary.
Okay, I just
Yep.
wanted to make sure beforehand.
Yep, absolutely. Yep.
I would have used that. I would have used that.
Yep.
I only found out because I was looking through Stack Exchange stuff because
Mhm.
I haven't coded in C, and even though the fundamentals are there, I didn't know the exact commands. And
Yeah.
stumbling upon UN64 max.
Yeah, it's a part of the definition of the standard integer.h. So any any definition within the header file you can use. Yep.
Yeah.
Yeah. Go ahead.
Uh, why didn't it work when I tried running a for loop
Uh-huh.
and actually creating the number that way?
Okay.
It just wouldn't work. It just stay at 0. I
Hmm.
initialize big number to 2. I run a for loop from I
Mhm.
equals 0 to 63.
Okay.
And
Well, I cannot take a look at your program right now, so we can do that maybe during the lab time. So before I forget, because I tend to do that, um, the record is on, so we are good. So I do want to share with you the new assignment, which is positive exponent, which is the going in the opposite direction. But I do want to do some editing before I release the positive exponent assignment, which is right here. I can show you, but I need to make a few adjustments, just because of the description is a little bit outdated. All right, so this is the positive exponent. I'm going to get rid of the first sentence, because you have your code already. So we don't need to use this archive. And I'm just going to change everything to get rid of the first sentence. So edit the file from the negative exponent lab and implement the same function, which is E10 to EXP2. Um, all right, so the two mechanisms should not interfere with each other. One is starting with a negative exponent, the other one is starting with a positive exponent. So if you set up your loop in the correct way, the logic of the two programs should not interfere, even though they're in the same subroutine. Because one starts with a negative exponent and the objective is get it to 0. The other one starts with a positive exponent and the objective is get it to down to 0. So those two loops, should not interfere with each other in any way. And I'm just going to say here, okay, the mantissa is also known as the coefficient. Just a name thing, just so that we know what we're talking about here. EXP is also known as E10, and then EXP2 is also known as E2. So this will facilitate, basically make sure the rest of the discussion is actually applicable to your program, because I changed the name of the members within the structure, but the rest is pretty much the same. Um, And obviously, I don't want you guys to use code blocks anymore, so I'm going to remove this instruction here. I mean, if you want to use code blocks, that's fine. But on the other hand, you should know how to do it without using code blocks because you just got the negative exponent assignment done. So whatever tool you use to get the previous assignment done, continues to use the same tool for the next one. That's all I'm gonna say. So if you have set up your VS Code, hey, keep using VS Code. If you have code blocks already set up, you already know what to do. Okay, so that's fine. If you use online GDB, which is my preferred method, that also works. Okay, so yeah, go ahead.
Is there a is there a log file in this one?
Yes, there's one. Except it's not a log file. It is actually part of the description of the assignment. But it's the same thing. Okay, it's showing you if you use the same input, which is dash n 1.23456 7 8 9 times 10 to the power 30, then the exp10 and exp2 and also the mantissa, which is now called a coefficient, they should be changed in the same manner. So this gives you a way to debug your program because you can basically just go through a few iterations of the inner loop, a few iterations of the outer loop, and compare whether your program is coming up with the same value as the exponent, as well as the exp10, the exponent of 10, and also the exponent of 2. So this is given to you already as a way to help you debug your program. All right? All right? So with that said, I think there's not much I need to talk about this. So it's time for me to release it. So let me get back to, update question. This is really annoying because if I don't click that button, Canvas completely forgets that I have made changes to the questions and did not warn me either. It will not warn me and say, well, I see that you have made changes to one of the questions. Do you want to save it? No, it would just quietly ignore all the changes to the question. Fantastic, right? So, hmm?
It's just Linux. Well, at least Linux warns you.
Linux warns you about stuff that is going to be quite destructive. The less destructive stuff, it doesn't care. But if you do a rm-r without the f, it would actually confirm with you and go like, "Are you sure? Because this is going to nuke the entire folder. Are you really sure this is what you want to do?" And that's what the f is for. The dash uppercase r, the f is force, which is basically saying, "Yeah, I know what I'm doing. Just do it."
It's like your confirmation button.
Yeah, automatic confirmation. Yep. From here on, don't ask me. I'm good with this. Whatever you're gonna do, I'm good with it. All right. So I'm gonna save and publish, and now you have access to the positive exponent assignment, which is also going to be, which is due in 1 week. I don't think it will take you 1 week anymore because once you have done the negative exponent, the positive one is more or less the flip side of it. Not exactly, but the logic is very, very similar to the previous one.
Yeah, I think for the positive one, I ended up getting it ended up being a little bit more complex, just to like get it out. But yeah.
Okay, yeah, it's structured slightly differently. Yep.
Should it only work with the positive or with both positive
It doesn't matter. When you turn it in for the positive exponent, the only thing I would check is positive exponent. When you turn it in as the negative exponent, I will only check it with a negative exponent. So you can completely take out the code for the negative exponent and only put in the code for the positive exponent if that is what you want to do. It should not be required because the two should not interfere because one is in the loop that says as long as the exp10 or e10 is negative, keep doing this, and then the other one is doing the opposite. All right. Any questions about this assignment? Okay. So if there are no questions about this, I can release kind of my solution to the whole thing, but I will do that during the lab time and not during the lecture time because I do have some other stuff that I want to talk about in the lecture time. All right. Oh, by the way, the exam one is fully graded, so you should see your grade in your grade book. Um, Just keep in mind that the thresholds for the letter grades are entirely different in this class compared to most of your other classes. So when you see, okay, if somebody sees 65%, of the entire score, that is not a failing grade. Okay, in this class, to get a B is 62.5 or more percent. So that means that 65% is legitimately a B in this class. So just kind of keep that in mind. Okay, if you get 40%, okay, it's not exactly the best grade, but it's a passing grade. It is equivalent to a C. Yep.
Are you gonna do the exam in one first?
Yes, but I have to scan it first, so that's going to take some time. Yep. So I'm going to scan every single answer before I turn it back. So this way I have a record of all the answers. Yep. Um, but I try my best to provide some feedback, in the quote unquote quiz in the assignments, because question 1 to question 6, each one is quote unquote its own assignment where you don't have to turn in anything. I'm only using that mechanism of Canvas to enter a grade as well as my comment. If the answer provided is too far off the mark, I would also give you a link to the document where I will explain the answer, or one of the way to answer the question. So you can also refer to that. All right. So I got something exciting to do today because I just wrote a module for this class just this morning. It's a really short one, but I think it is going to be quite useful for what we are about to do. And we can redo what we have done so far with the SR latch using the new method, just so that we know what it is about and how to use it. So I think at this point, I am going to, um, let's see, hide this entire module because we are pretty much done with that module already. So we are moving on to D flip-flop and other basic memory devices, which we started the other day. But what I wrote today is change propagation tracking. So I'm going to open this up just so that you know what this is about. Okay, it's a really, really short module, but it describes how we can systematically keep track of, oh, what is the state of that thing and what are we supposed to do in this step and so on. So you guys can open the page on your own computer so you can keep an eye on this document as I go back to talk about the SR latch. Is that okay? All right. So one additional thing that I would also do is to use a spreadsheet. I did this with the other class already. It's called SR Latch. You can find this document in um, the shared folder. It's just called SR Latch. But I don't want to reuse this because I want to do this interactively. So this way I can explain also interactively how to apply the technique to keep track of the state of each gate and also to track the changes of the output of the gates and so on. So yes, this is already available, but I'm going to start from scratch for today's lecture. All right. So that's what we're going to do. Okay, go to File, say New, and then another spreadsheet. Um, we'll call this one SR Latch, but for the Tuesday, Thursday class. Okay, so we'll say this is srlatch.txtu for Tuesday and Thursday classes. Okay, so the way we're going to do this is we're going to have one column per port. Okay, so the term port is basically referring to a point of something in Logisim that you can connect a wire to. Okay, let me just make sure that that statement is understood. So for every single individual point where you can connect a wire to in Logisim, it is called a port, P-O-R-T port. Is that okay? So now we have, the design that we talked about the other day has several quote unquote devices. S and R are just input devices. They're really simple. And then we have N1, N2. Those are NAND gates. So each one has 3 ports. And then we have the output pins Q and NQ. And once again, we have just the output pins. So they are very simple devices with only one single port. So the port of S, R, Q, and NQ, I just call those pins, because that's basically what they are corresponding to. And then for N and N1 and N2, excuse me, for N1 and N2, we have two input ports. And this notation was used in the previous lecture as well. So this time I'm just going to have one column for each port, input port, and then each one also has one single output port because N1 and N2 are NAND 2 gates. So the output of the NAND 2 gate is called the out port. So are we doing okay so far with what is in the spreadsheet right now? I have one column to track the state of each port in the design. It's good? Okay, all right. So now I can go ahead and try to use less space. And when you use any spreadsheet program, there's an easy way to do it. Just select the columns and you double click at the edge of the entire selection. And what that will do is it will minimize the width of the columns. It's pretty handy. I really like that feature. Um, and then what we'll do next is to kind of visually try to make sure that we understand that columns D, E, F are corresponding to one single device. And to do that, you go to Format, and then you can merge the cells that are being selected right now. In a real spreadsheet program, there's a shortcut key to do this, or you can use shortcut keys to get to it really fast. But in Google Sheets, it doesn't work that way. It's no big deal. It's just a little bit more steps. All right, so next, what we want to do is to express which pins are connected by wires. In other words, if you have a bunch of ports that are connected by electrically equivalent wires, they belong to the same node. So we want to be able to represent it in a spreadsheet too. So the way I'm going to do this is to basically just use the background color for the ports that belong to what we call the same node. Once again, a node is referring to a collection of wires that electrically are basically the same thing. Is that okay? Does everybody understand what a node is representing? Yes? Okay, very good. So from memory, I still remember, the S pin, which is the input pin, one of the input pins connects to the first input of N1. So I'm just going to use some color coding here and change the fill color of the cell. So this one I can choose kind of like a purplish kind of tint. The R pin connects to the second input port of N2. So these two are connected. So they're going to use another color. So the only reason why I'm color coding it is just so that visually we can look at this spreadsheet and kind of know how the ports are connected together. So the same color means the same node, so they are electrically connected. So the output of N1 connects to both the first input of N2 as well as the Q output pin. So all of these will now belong to the same color. So now I can go for the warm color schemes like yellow. And then the other three, which is the second input of N1 and the output of N2, as well as the output pin NQ, they're all connected as well. So now I will pick, like say, light red, like that. So now, the color of each port on the second row is also indicating how things are connected. Are you guys still with me? Everybody is understanding how this spreadsheet is currently set up? Okay. All right. So with all of this set up, everything starts with unknown. Okay. So I'm just going to put a question mark to every single cell. And then we go like, okay, so we know nothing about anything in the circuit. So the first state that we explored on the other day was to put a 0 into both the S and the R input pins. Both input pins started off with a value of 0. So that's what we're going to do next. So we'll say, okay, this is the initial condition or starting point, okay, however you want to call that, okay, starting point is fine. And then you want to say, input changes. So the input changes in this case is applied to both S and R. And I'm going to use boldface to highlight what is being changed. So this way it stands out and we can say, oh, okay, we just have to look for the boldface stuff. But when you look at the purple color of the S pin, you can see that N1 is also in the same color, which also means that needs to be updated to 0 as well, because the input pin S and the first input of N1 as a NAND gate, they are electrically connected. So that's why we also need to highlight this one. And then look at the R pin, which is in blue. There's one more column that is also in blue, which is column H. So now we have to remember that is also changed to a 0. And because it is a change from unknown, it is also going to be bold-faced. But for everything else, the question marks remain because I do not know what's going to happen next. Okay. So are we doing okay so far with row 4? Row 4 is what am I changing to the input and what are the immediate consequences of those changes. And when I say immediate changes, it is only because of the wiring. Okay, things that belong to the same node, they all get updated at the same time. Are we doing okay so far? So I'm just going to put a little remark on the side here to basically say spread changes due to node connectivity. Okay, just so that we can remind ourselves what's happening on this row of the spreadsheet. So the next one is going to be the more complicated one. So after a propagational delay, so we have started to use the abbreviation of PD of propagational delay. So after a certain propagational delay, I now have to question and ask, well, did the previous change one of the inputs of one of the gates? So what would be the answer? On between row 3 and row 4, did I change at least one of the inputs of one of the gates? I think so, right? Because if you look at in 0, it went from an unknown to a 0. So that's a change of at least one input of the gate that we know as N1, which is a NAND gate. And on the other hand, we also have the second input of N2 experiencing the same changes. So now we have to ask the question, what is going to happen to the output of N1? So I'm going to put an underscore here and also an underscore here as a placeholder so that I remember to kind of think about what should go into those two particular cells now that we can see at least one of the inputs have changed for those devices. Is that okay? Does everybody understand why I put this underscore as a placeholder to remind myself that I need to figure out whether there are changes to the output or not? Okay, very good. All right, so we'll just handle this one at a time. Okay, what should go here? the N1 NAND gate has one input being a 0 and then the other input being a question mark. Do I have enough information to conclude what the output should be at this point of time? This is after propagation delay. So that means N1 has enough time to respond to the input changes already. The question is, with one pin unknown and one input pin being a 0, do I know enough to conclude what the output should be for N1? Okay, it should be a 1. And we know that from a truth table. We talked about this in the previous class. So we know this one should be a 1, and same with this one here. So when you look at this one and you look at the previous stage, which is unknown, this is also a change. So I have to boldface everything that is a change. What about the rest of the system? Well, they can kind of remain as they were. So everything else remain as they were. And what we do next is up to you. Do you want to have a new row or do you want to keep the same row? In other words, right now, I can see that the output of N1 has changed. The output of N2 has also changed. But I have not followed the nodes, okay, to propagate the change here because of the connectivity of the nodes. So it's up to you to use the same row to make those changes, or you can use another row for those changes. So for illustration purposes, I'm going to separate into two rows just so that it's obvious of which row is doing what. So this one has to do with changes due to the nature of devices. In this case, we have NAND gates. And then the next row is going to basically propagate the changes of the output pins to other ports of the same node. So I'm going to say, repeat what I said here. Spread changes due to node connectivity. So now we ask, okay, we got this one being changed. What else is yellow in color? This one is yellow in color, so is this one. So they should all be bold at this point because they're all changed from what they used to be. And then we ask, what about this one here? It got changed. So what else is red in color, or what else is highlighted in red? So we go like, okay, we got this one and also this one here. And they all have to be highlighted in boldface because they are changes from what they used to be. Hmm?
Out did not change.
Huh?
Out did not change from the propagational delay to the
That is correct, but it is still a change from the previous one.
from the start.
Yeah. So in reality, row 5 and 6 should be combined, but I want to separate those two because one has to do with changes because of the way a gate functions, and then the other one is just because of node connectivity. If the output of one of the ports connected to a node changes, then all of the other ports connected to the same node should also change. So I'm separating it into two different rows, just because this makes it kind of obvious which one is which one. And then the rest would still be, 0, 0, 0, and then we have a 0 here. Okay, so now the question um, is at least one input of one device um, being bold-faced on row 6 at this point? The answer is, yeah, well, we got this one, which belongs to the second input of N1, and we got this one, which belongs to which belongs to the first input of N2. So they just got changed. So that means I am not done yet, okay? Because I need to make sure, I need to understand what these input changes will do to the device. Are they going to change the output of the devices where the input is already changed? So once again, after a single, after a propagational delay, now I need to ask, well, since we saw that one of the inputs of N1 getting changed, now I have to ask, is the output of N1 going to change as a result? And over here, it is the same thing because we saw that one of the inputs of N2 changed before. So now we have to ask, is the output going to change also because of that change? Now, if you look at it this way, then you say, well, N1, now we know both input pins of N1. One is a 0, the other one is a 1. And one look at the truth table says, well, the new output is going to be, it's going to be the same as before. It's still going to be a 1. Same thing over here. So these two ones are not going to be highlighted because it is not a change from what it used to be. So I'm not going to highlight it because it is not a change. All right, and then everybody else stays the same as before, because remember, this row is only reflecting changes due to the nature of devices. So I'm gonna copy and paste that sentence over here, and we have to do one more thing, but it is not going to be meaningful anymore, because we have to now say, okay, do I have to spread the changes due to the node connectivity? The answer is there's nothing to do. None of the output ports of the devices got changed after the propagational delay. So there's nothing that I need to worry about due to the node connectivity. Does that make sense? Okay. So that means at this point with row 7, we have reached what we call a steady state. In other words, there are no more changes to track. Everything is now stable. Is that okay? All right. So I'm going to do the one where we change both input pins from zeros to ones. Remember, that is what that's leading to. Can someone remind me what happens when you change both S and R from 0, 0 to 1, 1 together at the same time? Yep.
There's an oscillation that occurs.
It should start an oscillation, right? So we want to see how we track that oscillation now, okay? So now the next phase, or the next step, is to say, okay, the starting point is the same as what the ending state or the steady state from the previous step. That's going to be our starting point. Starting point or initial state, doesn't matter how you want to say it. And then we make some changes to the input pins, and we want to make both S and R ones together at the same time. So we highlight these, we boldface these two, and then we spread the changes due to node connectivity. So I'm just copy and pasting this sentence here. So now we have to look up the purple ones. This is in purple, so it has to be updated to a 1. And then we have to pick up the other blue one, which is over here. That one is also changed from a 0 to a 1. Are we good so far? Okay, this is just spreading the change due to node connectivity. And then everything else can remain the same as before. Now, whether you just kind of repeat like what I did here to copy things that did not change or just leave it blank is up to you. But leaving it blank has one problem, which is, if you are really further down here and then everything was blank, then you have to look all the way up to see what was the last change to that particular port, and that can be tedious, okay? But sometimes, you save a lot of typing. It's also good in that way. So now we have to say, okay, the question is, did I just change at least one of the input ports of a gate? That's the question. Well, not only one device, right? Both NAND gates just got at least one of their input pins changed. So that means I have a question now. The question is, since I changed the first input of N1, is that going to affect the output? I need to answer the question. Same thing applies to N2. So I have these two underscores for the time being as placeholders of something that I need to figure out. Is that okay? Yes, question.
On the first one, like after second um, delay, progression delay, why is like input one and the N1 no and is changed?
Can you refer to the row number?
I'm sorry, row number 7.
Row number 7?
Yeah.
Oh, you mean this one?
Yeah.
Oh, I forgot. Yeah, that's my mistake. That was my mistake. So that means I need to turn those to ones. Okay, very good. Thanks for spotting the mistake. And same thing over here. Yep. Okay, very good. So I forgot to, I copied the rows incorrectly, so that's potentially a problem. Okay, so very good. So now that we have fixed that, we can now come to the right answer for this particular question. Is is the output of N1 going to change now that both inputs of N1 are ones, and N1 is a NAND gate? Yep, it should change to exactly. Okay, so this is going to change to a 0, and 0 is not the same as what it used to be, so I need to highlight this 0 to kind of know that that got changed. Same thing applies here. It is going to change from a 1 to a 0, and as a result, I should highlight that. And then everything else, I'm going to keep the same, except for the, oh, wait, no, I cannot do that just yet, because at this point, it's time to these are due to changes due to the nature of the devices. So I will keep everything else the same. Is it okay for me to combine um, the changes due to the devices and the changes due to the node connectivity onto one row at this point? Or do you guys still want to see it as two different rows? CS2? Okay, okay, we can do that. So now we basically copy everything from before. And now we want to spread the changes due to node connectivity, which is basically just following the colors. And at this point, I'm going to show you a really nifty trick with almost every single spreadsheet program. You can do this, is to split the screen into two halves so you can scroll one without affecting the other one. That makes it easier to keep track of, the header, makes it easier, right? To see, which cell is corresponding to which header. Um, I do not have fine control over this. Like one scroll is gonna be too much. Um, okay, maybe I can use the scroll bar to have finer control. Slightly better. Okay, I think this is good enough. All right, so now we have to follow the colors. So all the reds are going to be changed because of this 0. So this is going to be a 0, this is going to be a 0, and so is this one. And they all need to be bold-faced because they are all representing changes that I have not spread due to node connectivity. This is what I'm doing right now at this point. And then the other change is this yellow out. So now I have to change all the yellow ones to zeros as well, and they also need to be highlighted because they are reflecting changes from what they used to be. And this is after a propagational delay, and now everything else should be copied. I just have to be very careful when I copy because last time when I copied wrong. Okay, so at this point, the next stage is to look at changes due to the nature of devices. So the first question I need to ask is, um, is at least one pin, input pin of at least one of the devices changed from the bold phase changes? So we look at all the bold-face changes and we say, yep, I can see this one is changing the second input of N1, and we can also see this one is changing the first input of N2. So now we have to say, well, since we have changes to the input pins, we need to make sure that we need to find out what's going to happen to the output pins of the devices where at least one input got changed. Does that make sense? So now we put an underscore here and we put an underscore here because we want to find out, are these two going to change as a result? Okay, so we'll handle one at a time. We'll handle this one, which is the output of N1. We do know both inputs of N1 at this point. One is a 0 and one is a 1. So what would be the output of N1 at this point of time after the propagational delay? It's going to be a 1 because at least one input is a 0, so the output is going to be a 1, and the same thing applies here. Since we are separating the spread changes due to node connectivity, this particular row is only going to reflect the changes because of the nature of devices, and it is after a certain propagational delay from the previous row. So I just need to kind of make sure that everything is reflected correctly here. So this is both phased, that's both phased, everything else stays the same, like so. And then the next one is going to spread the changes. So spread changes due to node connectivity, which is basically just following the color. Okay, I think I know how to scroll this like in fine steps like that, right? So now we have to spread the changes, which means we are following the colors corresponding to everything that is in bold phase from the previous row. So red, they all get ones, okay? 1, 1, and 1. And they all should be highlighted because every single one of those was a change from before. And then the other change was the yellow out, which is the output of N1, that got changed to a 1. So everything that has a background color of yellow should also change. So that we this, and also this one over here. Once again, they should all be highlighted. So I'm going to bold face, bold face, bold face. And then for everything else, they maintain the same as what they used to be. So we got 1, 1, 1, and also another one here. At this point, I can stop. Why can I stop? Because I understand that this is the same as row 11. Okay, so let me highlight those two rows, and you tell me whether the entire um, device is in the same state or not. So now we're getting back to row 11, which means we are looking at the beginning of the next cycle of oscillation, because the rest of the rows is just going to be a repetition of what we have already worked out. And that's why we know this is going to be a oscillation, because after one cycle, we got back to one of the states from a previous one, and so we know it's not going to end. Is that okay? So the point of this particular exercise is really just to make sure that we understand how to track the changes using a table, using a spreadsheet. Because I guarantee this is going to be one of the questions in exam 2. So, sorry?
Oh, sorry.
Oh, okay. So this is going to be one of the questions in exam two, which means you probably want to practice this. So what do you do to practice this? I got some ideas. So if you go back to the notes and go back to D flip-flop and other basic memory devices, it has quite a few devices that are described in this particular module. And let's see. So we're going to get to, say, D flip-flop, okay? This is the description of a D flip-flop, and obviously we have quite a few more devices, but the connectivity is still going to be specified the same way. I can help you set up um, the first row, okay? And I think it's a great idea if you can, kind of work out how it is going to work. I can give you some examples, and then you guys can kind of use what we did today to exercise, how to do this using a table. All right, so I will set up the exercise. You guys can basically, take the exercise and then actually fill it in with the individual values. Okay, first thing is, look at this thing here. I mean, how are we going to construct this? Well, step by step, just like everything else. Okay, so we're going to look at this document here, and I'm going to take this out in its own window, so this way I can look at, well, there are several ways to do this. Let me think about how to do this. Okay, I think I know how to do this. So what I'm going to do is to start a new sheet only for this class. And what I'll do, instead of having to kind of go back and forth, all the time, which can be confusing, I'm just going to copy and paste this stuff into the spreadsheet. So this way I can refer to it in the spreadsheet without having to without having to kind of flip-flop too much. But then I have to find out, where to put it because I think I need quite a few more columns this time than last time. So I'm going to stash it all the way over here and then go like, well, then you have to scroll back and forth, left, right all the time. No, I don't, because I can do the same trick here. You can split a spreadsheet or the display of a spreadsheet using this bar here, and it will synchronize the rows, but the columns are going to be split, so you can now control which part of, you know, how you want to split the screen. I just scroll the wrong part. I can move the boundary here, and I can say, okay, let's move it all the way to the right hand side like that, and then kind of line up things again over here.
Can you do both at the same time?
Hmm?
Can you do both?
Yes, you can. Yes, you can, because you can now also split it like this. So now you have four quadrants. Now the vertical scrolling of these two quadrants would be synchronized. When you use the vertical scroll bar, and then it will also be synchronized between these two if you use the scroll bar here. But the horizontal scroll bar is also separated into two halves. So you have supposedly you have one half over here. It's supposed to have its own scroll bar, but I can't see it. This one has one, and I'm not sure why this one does not show up with a scroll bar, but it's supposed to have one too. All right. Okay. So now we're gonna make the whole thing. Um, the first column, I will still kind of reserve it to kind of document what the row is trying to do. So now we just have to name the devices. And usually I would start with the input pins. So we have E and D and EN as input pins, and they only have one port. I would just call those ports pins. And then we have a NOT gate, which is known as N. And a NOT gate has two ports. It has one single input port and one single output port. And then we have N2 and N1. So we have N1 and N2. They're both NAND gates with two inputs. So once again, we have input 0, input 1, oops, input 1, and an output. And I'm running out of space on this side. So I want to scroll on this side without affecting the other side. But it's not letting me do that because as soon as I move over, it changes the other quadrant, which is not what it's supposed to do. Okay, I think Google made has a bug here because I'm supposed to see a scroll bar on this side, but it's not showing up. Um, Not really sure why. Hmm? I suppose. And if you want to add multiple columns, because I know that I need to add 3 more for N2, 4 more for the SR latch, and 2 more for the output pins, because we got 2 output pins. So how many are there? 3 plus 4 is 7, 7 plus 2 is 9. Um, okay, this is how you add new columns in Google Spreadsheet, is however number of columns you need to add, you highlight that many columns first. And then what you do is you right click and then you say insert 8 columns to the right of what we have here. So this is, this way you can add 8 columns at a time. And it doesn't fix the problem because I still cannot change the column, without crossing over to the other quadrant. It's supposed to scroll, but it's not scrolling. All right, looks like I have a bug report to do today, but that's okay. I can still remember what I need to do, fortunately. So we have in 0, in 1, and out for N2. Um, and then what do we have? We have the SR latch that we call SR. And an SR latch has inputs S, R. It also has outputs of Q and NQ. So this time we are not going to look into the internal mechanism of the SR latch. We're treating the SR latch as a device where the inside is basically a black box. Okay. And then we got what? The output pins, right? So the output pins would still be Q and NQ. And because they're output pins, they would just be named pins, like so. All right, so now we got all the ports done for this design. Come on. There we go. Okay, now it looks a little bit better. Now we need to work with the connectivity. We have a lot of nodes, so I'm not really sure whether color coding is going to work in this case because you need to differentiate between 7 different colors. So I will try anyway, okay? Because you can always just make a design in Logisim and slap the design here, but I want to do it using just the color scheme. So now I look at D as an input pin. I look at N1 dot in 0, and I look at N dot in. These 3. I'm looking at this part, by the way, okay? This is defining a single node, so that means everything named in that node belong to the same electrical connection, so they're going to use one specific color. So I'm going to put green in this case. The next line is connecting en.pin to n1.in1 to n2.in0. So these 3 belong to the same node, and as a result, they share the same color. And I'm going to use light blue in this case. The third one is n.out, which is here, and it connects only to n2.in1, which is here. And we'll pick a different color. Let's try orange. And then we look at the next one, which is n2.out. That connects to the S pin of the SR latch. So these 2 are connected. And we'll pick yellow. Let me see. It's good enough. Yellow and orange are, that you can differentiate between those 2. And then we look at the output of N2. It connects to SR.R, which is this one here. Right click. Oh, no, not right click. Control click and then change the color to purple like that. And then we have Q and the Q output of the SR latch connects to the output pin Q itself. I mean, this one is not super important, because it's just, so that we can report back the output of the entire design. And this one belongs to the same category. and we have to pick yet another color. Oh, I think red is used, but orange is used too. Green is used. Oh, we can just pick gray. Okay, we are running out of colors. So there you go. This is the setup of the whole thing. So the color is indicating the connectivity. If you're colorblind, just you kind of have to work with a slightly different color scheme because I know someone who was colorblind, and he basically said, yeah, when you see a picture like this and you can see like clearly there's this and there's that and there's that, I see only one thing because because I cannot differentiate between those colors. Yep, go ahead.
Yeah, so is there, like, I'm confused. Are there three inputs, D, E, N, N, or what
Say
are
that
the,
one more time.
are there three inputs in this case, D, E, N, or how does it exactly?
And is a negation port. It's a negation gate. So you can see right here, and is a NOT gate.
Okay.
So it is just whatever. If the input is true, the output is false. If the input is false, the output is true. So it's just a NOT gate.
But D and E N are equivalent to the SNR, right?
So both of these are input pins. So these two are input pins. These two are output pins, and then the rest are components inside. All right, so this is the setup, which means initially you can basically say we know nothing about what is in the state. Okay, so you can start with one starting point is to basically say we do not know anything about any port of the entire design. And I would just go ahead and remove this split here. And then you want to do the input changes, like input change. Um, make D equal to, I don't know, 0. And En is unknown. So that's going to be one thing, just kind of figure out what changes is going to propagate through here. So that's one exercise. And then the next one is going to take whatever is after this entire step. And then what you want to do is to change the EN pin. Oh, let me put a 0 here. So the other one is to change just the EN pin from a 0 to a 1. So let me just kind of describe that one. So with this one, the only change is going to be here. Change this. And these, I cannot put question marks here anymore because they should reflect the final state of whatever this step is going to entail. Is that okay? Does everybody understand what I'm trying to ask you guys to do? Are we good? All right. So I would highly encourage people to do this as an exercise because this is going to help you understand how we figure out the changes of between the gates, between the components, and also, how this particular device is going to work. Is that okay? So the way it works is actually described, well, this one may not be described in the notes. That's why it makes a very good exercise, because by doing this, then you start to understand how it works. Now, if this is a little bit too easy, because it really is not that bad, the next thing you can do is to say, okay, we're going to look at another input change. In other words, you have to copy whatever is the last state to this portion. So this time, what we want to do is to change D from a 0 to a 1 without changing the En. Okay, and then you can see how that's going to change the whole thing. So if you do this a few times, then you'll be good at tracking these changes. Are we okay so far with this? All right. So that's going to be a recommended exercise for you guys. Once you're done with your positive exponent, I would work on this, okay? Because it's going to be very beneficial to in your exam 1. Yep, exam 2, sorry. Yep.
Can we get this spreadsheet in the shared folder?
I think it is already in the share folder. Maybe not. Is it not?
I iterated it from the file new file.
Hmm. All right, so let me see if I can move it into the shared folder. Oh, so I created this in my root folder. Okay. All right, so let's move that into the shared folder. And I'll just put it here. There we go. Sorry, I didn't know it was created outside of the shared folder. Yep.
Have we done the role yet, or is that still active?
Sure, we can do the row thing. Oh, look at all these people popping up. I like the animals. Anonymous liger. Is that a cross between a lion and a tiger?
Yeah,
Yep.
It's infertile.
Kind of like
Yeah.
golden doodle, or I guess it's a mule type of bird.
It's also bigger than both, right? It's bigger
Yeah,
than the
yeah,
parents.
yeah.
Yep. That's what I remember. It's bigger than both, but it's also not a good hunter. So if you were to release it in the wild, it doesn't do as well as lions nor tigers.
So I'm pretty sure it's a mule. It can't reproduce.
Mm-hmm. All right. So what was the question? Oh, right, taking roles. Yes, let's do that.
Just wanted to make sure I didn't miss it again.
You did not. I missed it. All right, so I'm going to pick this one up and give you the answer. Okay, first of all, we change this 20221011. And the question, edgy flip-flop. Okay, I'm going to write it down here. Edgy flip-flop.
There's two.
All right, so let me change the date. Okay, how long would it take you guys to enter the text edgy flip flop? 20 minutes? 3 hours.
It's gonna take at least half an hour.
Because somebody's going to go,
That's a long passcode. I don't know if I'll be able to do that.
well, because somebody's going to go to Amazon and look for edgy flip flop.
Is it those like flip flops that the samurai used to wear, like the clogs?
Yep, the clocks.
The clogs almost.
You can buy those, but I cannot imagine those things being comfortable in any way.
I can't imagine. Also, like it'd be a bitch to run in because like they tilt and you get like the worst
It's edgy.
broken ankle of your life.
Yep, you cannot roll. There's no rolling whatsoever.
Rolling.
Edgy flip.
Edgy flip flop. If you enter incorrectly, just let me know. I will still count you as present. All right, so I'm going to go back to the notes because there's a lot more to the D flip-flop module than what we have just talked about. So this is why we have the edgy flip-flop, because we have a device that not just me, okay? This is industry standard name. It's called an edge sensitive D flip-flop, okay? D is data, okay? D flip-flop, the D stands for data. EN is enable. Okay? So so let me give you an idea, okay, what it is going to do. But you still want to go through the spreadsheet exercise just to understand, how it gets the job done. So let me go to Logisim. So let me start up Logisim first. And then we'll talk about, how it works. So I'm going to start up Logisim, which is Java-R jar, Logisim310, and I'm going to create that device from scratch. Okay, so let's see how much I can remember from what we just did. We got two input pins. One is D, and then the other one is EN. And then we got a few gates, right? So we got a NOT gate, and we have two NAND gates. So we pick up two NAND gates. Okay, change the input to 2. make it narrow, like so. And I don't have a SR latch, okay? There is an SR latch in the memory device, but it is not the one that you want to use. Because this one, they have a SR latch or SR flip-flop, which is how they call the SR latch, but it's not the one that we want. So I'm gonna have to construct an SR latch myself. It's not that big of a problem, because we already know the SR latch is a very simple device with two input pins, two output pins, two NAND gates in between. Okay, so I'm just trying to fast forward this whole thing, and I'm too lazy to redo the NAND gates, so I'm just going to copy it between circuits. Right, there we go, and stash it about here. Yeah, it doesn't line up exactly, but close enough. Oops. There we go. And then the output goes here. And then the output goes here. And then we have the crossover, right? The whole thing, the cool thing about an SR latch is it's a circuit where the output of something goes into the input of something else and vice versa. Yes, I'm making it unnecessarily ugly, but that's okay because it doesn't change the functionality. All right. This is what happens when you have an engineer to design a car. Nobody wants to buy it, but it may be the most reliable car ever on the road, but nobody's going to drive it. All right, so this is the SR latch, and so go back to the main design, pick up an SR latch, stash it here. What else do we need? Two output pins, I think. So we got two output pins, like so. One output pin is Q, the other one is NQ. I have no idea why Q is used as the typical output label of a gate. Um, so I have no understanding of why that convention is used. So now we have to hook up the stuff in between. So I'm going to go back to the spreadsheet because I really cannot remember. So we are still looking at a regular D flip-flop in this case. So we can see how D goes to N1, the first input of N1 and the negation gate. Okay, so there we go. So we have this one as N1. And this thing here. So that goes here. It also goes here. And then next we have En going to the second input of N1 and the first input of the second NAND gate. Okay, so this guy goes here and also there. All right, and then we have the output of the NOT gate going to the second input of the second NAND gate. Yes, this is starting to look kind of ugly. And then we have both of the outputs going to both input of the SR latch. So here's our SR latch. And make all the connections. And then the output of the SR latch goes straight to the output pins that are labeled in that particular way. And yes, those wires are red for a reason. So why are these wires red? Because look at the SR latch. What is the state of the SR latch? Both inputs are ones, right? So according to what we talked about last time, when both inputs of the of an SR latch are ones, what is it trying to do? Maintain the previous state, right? And I did not set the previous state of the SR latch. So the SR latch at this point is totally confused because it's saying, but you didn't give me any known state to begin with, and you're asking me to say, okay, remember the previous state and show me what your previous state is. It just says, I cannot give you that because I really do not know what the initial state was supposed to be.
What's up? Oh.
Hmm?
Sorry, you can go first.
Go ahead.
So it's two SR latches connected to each other,
No, we have one single SR latch,
one single one.
one single SR latch, and two NAND gates. The two NAND gates are not constructing another SR latch at all.
Okay.
Okay, go ahead.
I was gonna say, would there not be an initial state because like if there's like maybe a propagational delay?
Well, as I,
Because
because because the moment I slap the SR latch into the design,
yeah.
it starts with everything being unknown. But the moment I actually made connections to it, both inputs were ones. So it never got a chance to experience only one of the pins being a zero, the other one being a one, which is how we set the state of an SR latch. It never got through that stage. So if you do a right click on the SR latch and say view SR latch, this is what it says. Both input pins are ones, but since I did not know the output of the initial output of the first NAND gate, nor the initial output of the second NAND gate, so now the output remains unknown because this thing is going back to here. This being a one by itself is not deterministically telling me what the output of the NAND gate is supposed to be. It's not doing the flip flopping. It's not doing the oscillation either. It is simply unknown at this point. It's basically just saying, I have no idea what I'm supposed to be.
What would happen if you did that with like an actual circuit, like a short circuit, or what would happen?
No, it would just oscillate.
Oh,
Yeah, you're just making a square wave generator, and the frequency of the square wave is dependent on the because the whole idea is the moment you change the input pins, it's going to take a delay in order for the output pins to be changed. That particular delay is the halfway through the cycle. So if you multiply that propagational delay by 2, then you get the period of the oscillation. And the frequency is 1 divided by the period, so you can also derive the frequency once you know what the period is.
that's cool. That's cool.
Yeah, you can actually build this. You can actually build the oscillator and actually use an oscilloscope to see it oscillate.
That's my favorite part about this class. You can
Yeah.
exemplify it in real life too.
Yep. It does I think it can get warm, but not hot, because all that, flipping on and off, a MOSFET at the end of the day is a capacitive load. So it basically you're charging and discharging, charging and discharging a very small capacitor. So you're still going to heat up the device a little bit, but I don't think it's going to be to the point where it's hot to the touch. It may be warm to the touch, but it's not going to be hot to the touch. But it will still be fun to build it and have an oscilloscope and hook it up, and actually see the square wave going.
This circuit's having a seizure.
Well, sometimes an oscillation is good because we do build oscillators intentionally. It's just whether it is what you want or not. All right, so getting back to the main part of this design. So the D port here specifies what do you want the device to remember. That's the job of the D port, is to specify what do you want it to remember. It's a 0 or a 1, okay? And EN is level sensitive, which means EN being a 0 means the device is not paying attention to the input. When En is a 1, then Q would reflect whatever D is, and then NQ would be the negation of whatever D is. All right? So let's observe that, right? Let's observe that and say, okay, so En is a 0 right now, so I should be able to change D all day long, and nothing is going to happen to Q nor NQ because it is supposed to be not paying attention to D at all. So I can now flip this all day long. See how it's not affecting the SR latch? And that's a very simple, it's a very simple mechanism because EN is connected to EN not negated is connected to at least one input of N1 and at least one input of N2. So as a result, if EN is a 0, N1 and N2 has to output a 1, regardless of what the data is. But the output of N1 and N2, they're connected to the S and the R input of the SR latch. And we already know that when both inputs of this SR latch are ones, the SR latch is basically saying, I'm not paying attention, I'm not changing, I'm just maintaining the previous state. So that's the, analytically speaking, that is the reason why when En is a zero, the SR latch just doesn't pay attention at all. On the other hand, if you turn En on, then you can see immediately how the SR latch Q is reflecting the D input pin. The negation gate here is necessary because we want D to affect the S pin and affect the R pin in opposite ways. That's why we need a negation gate here, because the way we want to affect the S gate and the way we want to affect the R gate would be opposite to each other. As long as En is on, and this is why it's called level sensitive, because as long as En is a 1, when you make changes to D, it will eventually change Q and NQ. So you can see how the change is almost instantaneous, even though once we analyze using today's lecture, using today's technique, we will actually see that it takes a few propagational delay to get the output to change, but from our perspective, it seems to change immediately. Are we good? Okay, are we understanding this particular design? Okay, yep.
What was the NQ for?
NQ is simply the negation of Q.
Why?
Sometimes it is useful, that's all I'm gonna say. Sometimes it's useful to have NQ because it's free, right? Because the SR latch, by the nature of the SR latch, it has the negated Q as an output. So since we don't know what we're gonna do with the D flip-flop, we're just gonna let it stay for a while. But otherwise, you're correct. It doesn't seem to do much, doesn't seem to be useful at all. Are we good so far with this design? Okay. Let me take a look at the time. We got 8 minutes. So I think we got enough time to build the next one, which is an edge sensitive D flip flop. And that's why I chose the word for today's road taking to be edgy flip flop. So this one is slightly more complicated. It has one NAND gate that has 3 inputs, one NAND gate that has 2 inputs. It has 2 SR latches. So we have S and C as SR latches. It has one single output pin Q. So NQ is lost in this case. We don't need to keep track of NQ. All right, so we are going to make this particular design and see what it means when we say edge sensitive. I think we got enough time just to do that. And so that I don't have to flip-flop between the two, I'm going to do this trick here. I'm going to open it up in this particular program, and I want to change it so that it's always on top. So this way, even when I go back to LogicSim, this is not going to go away. So let's go back to LogicSim right here and build a edge sensitive D flip-flop. There we go. All right, so with this as a guide, I can now just go ahead and pick up the components. So I'm going to pick up 2 input pins, 1 output pin, 2 NAND gates. So go to gates, pick up NAND. There we go. The first one only needs to have 2 inputs. The second one needs 3 inputs. Okay, so duplicate. And this one is going to have 3 inputs. And I should name these things too, just so that I know which one is which one. This is N1, this is N2. And then we got, what else? 2 SR latches. Okay, so we go to the SR latch as a component that we just made. Name one as S, and then name the other one as C. Control D, and change this one so that it is C. And then I think that's it. We got everything. All right, so now it's time to connect the things. So this time I'm going to go, with this one, which is connected straight to the output pin. So we're connecting Q to Q like that, and this is our Q pin. And then we'll go take a look at. I'm just looking at the whole thing and see which way I want to make the connections. This is D or data, and this one is what we call clock. There we go. So the data pin goes to N2, the second input of N2. All right, so I mean I can start to align things just so that hopefully it will look good later on. And then the clock pin goes to the S pin, the R pin of the SR latch S, and also N1 dot in1. So that will be the middle pin of this guy here, and also the R pin of this one. Okay. All right. And then N2 dot out is going to in1 dot in2. So that will be this guy. This goes to here. All right. So things are starting to look a little bit ugly now. And it also goes to S dot S. So that would be this pin here. Okay. All right. Now we take the output of N1 and we want to connect it to the first input of N2, which is here. So this one goes all the way here. So if somebody is looking at this and go like, isn't that kind of like an SR latch? You'll be correct. We are actually using N1 and N2 to make an SR latch, but it's not just an SR latch because N1 has 3 input pins, so that's why it is not just an SR latch. And let's see, where am I doing? So we want this, and then C.R. So C.R is also supposed to connect to the output of N1. All right, so just go straight across like that. Now we take the NQ output of S, which is this one here. We want to connect it to N1.in0. That's pretty easy. It's localized, like so. And where else is it supposed to go? It's supposed to go to C.S, which is this pin here. There we go. Finally, we have C.Q to go to Q.pin, which is already done. All right, so I think I might have missed something because S.Q is not used. So did I miss S.Q somewhere? No? Well, I see no input pins left unconnected. I have one output pin from SR latch S that is not connected to anything, which is okay. That is not necessarily a problem. If I leave one of the input pins of something unconnected, that's probably a problem, okay? But if I leave an output pin of something not connected, including NQ of C and also S.Q, it is not necessarily a problem. It can be indicative of a problem, but I don't think it is. All right, so now we need to test it, okay? What does this one do? We still have data, which means, this is where we specify what do we want the circuit to remember? Do you want to remember a 1 or do you remember a 0? The output pin Q is the state of the entire memory device, so it basically always reports back and say, yes, I'm remembering a 0 or I'm remembering a 1, which now at this point it says, I have no idea what I'm supposed to remember because the moment the SR latch C is created, it starts with unknown states. And the way I connect the input pins is, both inputs are ones to begin with, so it never got a chance to set its internal state, and that's why it is unknown. All right, so what about the clock pin? So the best way to describe an edge-sensitive D flip-flop is it doesn't do anything except for the moment when the clock goes from 0 to 1. Let me say that one more time, okay? An edge-sensitive D flip-flop doesn't do a single thing except for the instant of time when clock goes from 0 to 1. When clock stays stable as 0, you can flip the data pin all you want. It doesn't do a single thing to the CSR latch. Once the clock is a 1, it also doesn't care. You can flip the D pin all you want, and it doesn't do a single thing. So let's go ahead and check it out, okay? So if I did the circuit correctly, which I think I did, even though I wasn't super careful about this, we'll see. So the data pin is now a 0, the clock pin is a 1, and according to what I said, the moment I turn the clock pin to a 1, then the output Q here should become a 0. Okay, so that's the theory. So let's check it out. Yep, okay. So the second thing I should also check out is because now the clock pin is a 1, it is not changing anymore. So I should be able to make changes to the data pin all I want, and nothing should happen to the output Q. Now, the internal states in terms of the NAND gates and the SR latch S, they might change a little bit, but nothing should change to the CSR latch or the output of Q. So let's check it out. The clock pin stays as 1, and then the data pin is flipping and flopping. Nothing happens. Very good. So now let's just say that I want to change the entire device to remember a 1 instead of a 0. So the way to do that is I have to change the data pin to a 1 first, which is specifying what I want the circuit to remember. Then I need a transition of the clock going from 1 to 0. Excuse me, not the other way around. The other way around, I need the clock to go from 0 to 1, which means this is another test. If I transition the clock from 1 to 0, nothing should happen to the output. So let's check that. Aha, okay, so even though there are some changes internal to the device, the output did not change. So now is the moment of truth because I can now turn the clock from 0 back to 1. At this particular instant, okay, it would change the Q output to reflect what the data input is. And there we go. But after this, I can now change the data pin again all I want, and it doesn't affect the output. So the behavior of an edge-sensitive D flip-flop and the behavior of what we call a level-sensitive D flip-flop, they are kind of related. One is kind of like, okay, here's an on-off switch. As long as the switch is on, whatever happens here transmits to the other side. That's a level-sensitive D flip-flop. The edge-sensitive D flip-flop is more like, well, okay, so I will gate the changes from the input, except when the clock pin goes from 0 to 1. At that instant of time, I will update the output. But any other time, I just ignore the input. So one controls whether, and are you talking to me? Do you want me to update something? That's level sensitive. The other one is asking, when do you want me to do it? That's edge sensitive. Is that okay? Because both are important, okay? When I said both, I'm referring to who are you talking to? Who do you want to update its state? That is important. But equally important is when do you want it to update? In other words, each one of these designs, each one addresses one issue, but they do not address both issues. So what do you think is the natural next design? Yes?
Put them both together.
Put them both together, yes. So we end up with a level and edge sensitive D flip-flop. When you have an enable, which is level sensitive, and also you have a clock, which is edge sensitive. So that's in the notes too, which means I think it's going to be a great idea if you guys can spend some time to read ahead of the class, because that's where we are. Okay, I have to go all the way back because okay. All right, so the other thing is once we construct the edge-sensitive D flip-flop, you have a bunch of exercises even within the discussion because you can actually go through what we talked about today about tracking propagational delay and whatnot, and you can use this as an exercise. Okay, use it as a starting point, and then go through the tracking of the changes. And then this one is the clocked and gated D flip-flop. And you can see the design is somewhat more complicated because this time we have three SR latches as components and then two AND gates. These A1 is and A2 are just regular AND gates. They're not NAND gates. Um, and then at one point, and then one last detail is the reset, because when you power up a computer, the SR latches are all going to go. I have no idea what I'm supposed to remember. So your computer, all the components in your computers wake up in a state of it can be anything, right? That would not be a good thing because you really want your computer to start execution at a certain place when you power it up. So that means we need a reset button or reset line to basically say as long as the reset line is a 1 in this case, the SR latch that is supposed to remember the state of the entire thing is going to reset to a 0. So this way we have a mechanism to force everything back to a known state. And then after that, I know the lecture is kind of over. And then after that, we basically build an array of the last design. And now we have a circuitry that can remember 8 bits. It is really just a gang of 8 1-bit D flip-flops. So you can see how, except for the data bit, which is split and fed into each one individually, everything else are shared. The EN, the clock, is shared. They all share the same clock. The EN is also shared. They all have the same enable. So all 8 bits will pay attention. If you want them to update, they update together. And the moment of updating is also at the same time. So this device can remember 1 byte at a time. You present the 8-bit pattern, and then you say, yes, I'm talking to you, and now I want you to remember that right now. That's where we are getting to in this particular module.
Computers are so cool.
I think so, because we can build everything out of transistors. The SR latches are built out of what? NAND gates, and we can build AND gates, OR gates, NOT gates out of NAND gates. So everything that we see today, I mean, yes, we do need a lot of P and N type transistors, but nonetheless, we can implement everything using transistors. And this is just the device to remember 1 byte.
This is just 1 byte.
This is just 1 byte. Yep.
You have to get a million of these just to store.
1 megabyte. Yep.
That's, yeah, it's 1, 2, 3, 4, 5, 6. Yeah, no, a billion of these to store a gigabyte.
Yep. A gigabyte is 1 billion.
And in just a 16 gig RAM drive, it would be.
Well, in reality, RAM is a little bit different. So this is a register. RAM is different in several sense because we use DRAM these days, not static RAM. Because static RAM takes a lot more transistors to implement. This would be a basic circuitry for static RAM.
So this would be like ROM or?
No. Static RAM is something that you use when you have low power consumption requirements. Then static RAM is nice because if you just wanted to maintain the content, it almost draws 0 current to maintain the content. Now, what we use in computers today, probably even cell phones, those are called DRAM or dynamic RAM. So dynamic RAM makes use of the capacitive characteristic of the transistors. And it goes like, okay, I'm going to refresh you. You're just going to use the capacitive property to maintain the state. So, but because it's capacitive and there's always leakage current, in the transistor's design, so over time it's going to lose track of its content. So that's why you need to refresh. Like every so often, you have to say, okay, refresh. You take your actual state, feed it back to yourself, charge or discharge the capacitance of that cell. But because of that, the number of transistors you need to remember 1 bit is much lower. So that's why DRAM has a much higher density when you need to fabricate it into a chip. Static RAM doesn't have nearly the density, but it has the nice feature of you don't need a refresh. You don't need a dynamic refresh.
Yeah, this is just, you just have the input.
Yep. Yep. As long as you don't touch that clock, nor the enable, it will keep its state without drawing and almost 0 current. But the dynamic RAM does need refresh, and every time you do a refresh, it does exercise the circuitry and it consumes more energy that way.
Still, it really puts it into perspective. Just to make one of those clocked and gated flip flops, you gotta have several different gates, several different inputs,
Yep.
and then you've got to put 8 of those.
Yep.
Just to store 1 byte.
Yes. However, this is what a register looks like. Okay, we'll get to registers when we talk about the processor itself. So this is what a register looks like inside the processor. Um, Memory and registers they seem to do the same thing of remembering things, but they're also very different in many other ways. The notebook that you're using right now to take notes in the class is more like a register. So what is equivalent to a location in RAM? A book in the library. Think about how much time it's going to take you to get the content of a particular page of a particular book from the library versus I tell you, okay, can you show me what note you took today? It's like, okay, here, right here, here it is, right? And I want you to update that sentence just there. You just kind of line it. No problem, done. If I tell you to do the same thing, to read a sentence of a page in a book in the library, right now, I'm gonna stand here and go like, okay, I think you'll be back in about 10 minutes. That is kind of, I mean, this is exaggerated, obviously, but that's the trade-off. The library can store a huge amount of data. I mean, your notebook, I mean, I know some of you are using iPads and it doesn't really apply, but if you're using a paper-based notebook, you can only store so much information locally because your backpack is only so big, right? That applies to RAM too. RAM, I mean, registers. So registers are really fast, easy to access, but you only get so many of those things, okay? You cannot have a whole lot of registers inside the processor. But in terms of RAM, you got plenty, tons over at the library. But to get to that content takes a while. Yep.
So, this is, you saying this is within the processor, would this be like the cache?
No, this is internal to the processor. This is basically a register inside the processor. Yep.
Registers is what we use in assembly language to store the data.
It is one of the constructs that you can access in software in assembly instructions. Yes, that would be correct. Yep.
So iCloud is like a type of register?
Sorry?
iCloud?
iCloud?
It's like where you store data?
Did you say iCloud?
Yeah.
Like,
or like Google Drive?
Google Drive is not. It's not even closely related to memory nor registers because it is a resource on the internet. You need I/O devices like network cards and whatnot, and then you need to go through the routers on the internet. So that's like accessing a book in one of the archives in one of the cities in China.
Alright.
Or make it Mars. Okay, let's say we have civilization on Mars. Well, I'm trying to get a page of information from Mars. That's more like iCloud. In terms of the scale of time. All right, so we are almost done with this module. I will go through this stuff here, on Thursday, but I think it is really going to be beneficial if you just go ahead and do the exercise that I suggested earlier. Now that this document is accessible to all of you, just go through that, with the content in the module and make your own exercise. And every time I say this is not going to be a graded assignment, at least a few people are going to say in their head, of course, not going to do it. That is a choice, okay? But what I'm saying is doing this is going to be helpful, okay? That's all I'm going to say. All right, so the lecture part is done. I'm sorry that I kind of went over time a little bit. So what you guys can do now is to stay here and work on your positive exponent assignment. Or if you have questions about the negative exponent assignment, I can help you, take a look at the program and see why it is not working. I think it is important to understand why programs are not working because the process of finding out why a program is not working is helpful. The process itself is an opportunity to learn something new. Yep, go ahead.
GDB sucks.
Why would you say that?
I didn't like it. It was every time I was using it, it was fighting me.
In what way?
Just, it wasn't very streamlined at all. It was,
No, that's not. It is not streamlined, but it gives you um, abilities to do just about everything that you need to do with a debugger. It's just not intuitive because it's not a GUI thing. It is a command line thing. Yep.
I have a question.
All right. Well, let me stop recording. Yeah, because I think we can officially say the lecture is over.